Hello guys, so welcome to our Tuesday lecture. So in this lecture we're gonna explore a new BGT amplifier configuration, which is the common collector amplifier. So we discussed the common emitter amplifier and we discussed also the common base amplifier. Each one has its own advantages and disadvantages. Okay, so the common collector amplifier, which we're gonna discuss today, has its own characteristics as well. So let's explore its amplification and our input and our output, and then based on our analysis, we're gonna explore or we're gonna know what kind of application we can use this new configuration in. So let's have a simple example for it. So let's draw an example for it. So we have here this is a simple example for a common collector. So we have here the input at the base. This is the input connected to the base. And here is the output. The output is connected to the emitter. So the output connected to the emitter. And since the collector has no input or output connected to it, so it's common for us. This circuit has also another name, and by the way, this is the most famous name rather than this common collector amplifier. It's called also emitter follower. Emitter follower. And we're gonna know the reason behind this naming, after we make our analysis and this find out the voltage gain of this guy, this new circuit. Okay. Good. So let's deduce or get the equivalent circuit, EC equivalent circuit of that circuit here. So here is the AC equivalent circuit of the transistor itself, beta IB. Oh, here is RE or RB, R by. Here is IB. Here is the emitter, here is the base, here is the collector. And we continue the other part of the circuit. So in EC, the DC sources are cancelled. So VCC will be connected to ground. So there's another color here. This guy will be connected to ground. So the collector is basically connected to ground. Good. Another DC source that we should cancel is the current source. So this current source should also be cancelled. So it will be open circuit here. And if it's open circuit, then you can just ignore it. And the capacitor will be short. So the emitter here will be connected through RL to the ground. Like this. Then we have lastly the base. The base is connected to our signal, then the signal, then the ground. Good. And before we continue, here is IB, here is beta IB or IC, here is IE, and here is VO. VO is the voltage across RL from the emitter to the ground. And the input is between the terminals of R input, and R input is between this point, the terminals of the source or the signal, input signal. So this point here and the ground. So this should be the input here between these 2 points. The base, this point, which is the base, and the ground. Good. So let's find out our, basic characteristics of any amplifier, our input, our output, and AV, the voltage gain. So number 1, our input. Sometimes I call it RI or RIN. All are the same. Good. So what is our input? So if we imagine, so basically our input is between these 2 terminals, this terminal and the ground. So it's equal to V input over I input, assuming that there is a current here called I input flowing in that branch here. So it's equal to V input over I input. Good. So what is V input? V input is the voltage between this point and the ground. So if we make a loop here, a loop like this, we find that V input is equal to IB R by, the voltage across R by, plus the voltage across RL. And the current in RL is IE, which is beta plus 1 IB. So plus beta plus 1 IB RL. So this is equal to, let's take IB as a common factor. So we end up with R by plus beta plus 1 RL. And I input is basically IB because they are in the same branch. So our input, if we divide these 2 together, will be IB R by plus beta plus 1 RL over IB. IB will go with IB, so Rn will be equal to R by plus beta plus 1 RL. We know that R by is hundreds of ohms to few kilo ohms. Let's say it's 1 kilo, okay? And RL usually, and beta usually in hundreds, 100, 150, 200. This is our typical values, okay? And RL usually also, we can say, let's say 1 kilo ohm. So if you would multiply 1 kilo ohm, which is RL, by 100, then this will give you 100 kilo ohms, okay? So based on that analysis, we now see that the common collector amplifier or the emitter forward circuit has usually very high input resistance. So this is the first advantage of the common collector amplifier, very high input resistance. And why is that? Because of the inclusion of beta here. So beta, because it's 100 usually, when it multiplied by something, it will be magnified 100 times. So this is, of course, will increase our input resistance. So this is the first advantage actually of the common collector amplifier. So good. So let's go now and calculate our output. So I want to go back. Yeah. RO number 2. RO. So RO is resistance seen by the load. So we must remove the load testing voltage source like Vx that produces Ix, and RO will be Vx over I. So let's do that. So let's draw the same circuit again, and we can just make a copy and paste of it to not waste our time. Here it is. So I'm gonna remove our load. And put a testing voltage source instead of it. So I'm gonna put here Vx, which reduces Ix. And of course, don't forget to cancel the independent sources, which here is the V signal. So we should also cancel V signal by shorting it. So we're going to replace this guy by short circuit. Okay, good. So RO is equal to, let's go back to the blue color, equal to Vx over Ix. Good. So what is Vx and what is Ix? So at that node here, Ix is going into the node, beta IB is going into the node, and IB is also going into the node. So Ix plus beta IB plus IB equal to 0. So from this, Ix is equal to minus beta plus 1 IB. Good. How about Vx? So if we take this loop here, let's enlarge it a little bit. This loop, so Vx is in that direction. IB is flowing in that direction, so positive, negative. Flowing in that direction, so positive, negative. So this voltage is that direction. This voltage is also in that direction. So all of them are the same direction. So Vx plus the voltage across R by, which is IB R by, plus the voltage across R signal, which is again IB R signal, equal to 0. So Vx is equal to minus IB R by plus R signal. Good. So both now Vx and Ix are a function of IB. So we can divide safely now because we know that IB will just go away. So Vx is minus IB R by plus R signal over minus IB multiplied by beta plus 1. So this will go with this, minus also goes away. So we end up that RO equal to R by over beta plus 1 plus R signal over beta plus 1. Okay, good. So or we can just, leave it like this. Both are the same. Some people also like to substitute R by over beta plus 1 with RE. You remember, guys, RE, this resistance in the other AC model for transistor is equal to R by over beta plus 1. So some people also like to write it in that way. Because RE usually, if you see, guys, here, R by, we know that it's a few hundred to kilo ohms, to few kilo ohms. So if we divide it by beta, which is, 100 or something, or even more than 100, then we end up with something in ohms. Okay. So usually, and also our signal, maybe it's 1 kilo, 2 kilo, something like this, even 10 kilos. then you will divide it by beta, then you attenuate or lower its value 100 times. So for that reason, RO, the output resistance of the common collector, usually very small. So let's write this in red. This is very small resistance. So till now, we find out that the common collector has a high input resistance and a low output resistance. And these are two, basic advantages of the common collector. Okay, let's continue and see. How about AV? Let's have another page. I don't think now we can continue here. Number 3, AV. AV is VO over VN. I will deduce AV now, and based on AV, we can get the open loop voltage gain. Okay, you remember, guys, there is voltage gain and open loop voltage gain, and open loop voltage gain is just the voltage gain when the R load is equal to infinity. I can do AV first, then AV naught or the open loop voltage gain, opposite to the way we did before. Before we get AV naught first, then AV, but we can do the opposite as we will see now. So VO over V input. So let's let's put the circuit again for our convenience. Good. So VO is the voltage across our load. So it's equal to the current in our load multiplied by our load. The current in our load is beta plus 1 IB. And our load is our load. Good. How about V input? V input again is the voltage between the source C at the terminals of the source. So the source is one part, which is V signal and R signal together. So it's a voltage from this point to the ground. So if we make a loop here, V input is equal to the voltage across R by plus the voltage across RL. So I will write it in that way now. It's IB R by plus VO actually. The voltage across RL is VO. So before I continue, I will just write this here before we continue. It's VO, and the V input is IB R by plus VO. And before we continue now, we know that EV is less than 1. So we got enhancement in our input because our input increased. We got enhancement in RO because RO decreased. But till this moment, EV attenuated or EV reduced. It's less than 1. It's not amplification. So this is less than 1 because, of course, when you divide something by the same stuff plus other thing, which is positive, then you'll get something less than 1. Okay? So let's continue and see how how far we reduced the voltage gain. Maybe this IB R by is small. Maybe. Let's see. So IB R by, and the VO is beta IB, beta plus 1 IB RL. This is VO. Okay. So let's divide those. EV is equal to VO, which is beta plus 1 IB RL over the input IB R by plus IB beta plus 1 RL. IB, all those guys go together. So we end up with beta plus 1 RL over R by plus beta plus 1 RL. And here is the trick. Yes, it's less than 1, but usually, beta RL is much larger than R pi. That's why so usually, let's write it, beta plus 1 RL much larger than R pi. Why is that? Because even RL is small, it will be multiplied by beta, which is, usually 100 or something, or even more. So it will be magnified 100 times. Okay. So based on that, this will be approximately most of the time. Of course, in any problem you solve, you should analyze it and get the accurate number. So usually close to 1. So it's not that attenuation. Okay, usually it's close to 1. And it will become clear now if we calculated the open loop voltage gain. So for number 4, the open loop voltage gain, which is AV naught, which is AV when R load equal to infinity or open circuit, right? So let's do that here. So let's divide the numerator and the denominator by RL. So we'll get up with beta plus 1 over R pi over RL plus beta plus 1. So if RL goes to infinity, we will end up with beta plus 1 over beta plus 1, which is 1. So it's clear here from AV note that, yeah, the voltage gain is close to 1. Even if RL is small. But because it will be multiplied by something in hundreds, like beta, then beta plus 1 RL will be much larger than R pi. Okay? How about the last stuff? Number 5, the overall voltage gain, GV. GV is equal to AV, R input plus R signal. So AV is close to 1. And our input is, let's write it down. It's, where it is, it's R pi plus, yeah, beta plus 1 RL. Over R pi plus beta plus 1 RL plus R signal. Again, if we designed the circuit such that beta plus 1 RL is large, and by the way, you can do that because you can choose a transistor, so you can choose a transistor with very high beta. Then, if our input is much larger than our signal, you will end up that GV is equal to 1. So it's not that bad. So you get enhancement in our input, you get enhancement on our output at approximately the same voltage input, the same voltage will be in the output. So you will not lose. Okay. So let's now put some observations, and based on these observations, we're gonna, determine which kind of applications we're gonna use this common collector. So observations. And let's good. Number 1. So we common collector has very high input resistance. Good. This is advantage. Common collector has very small or very low output resistance. And this is also advantage. Number 3, the voltage gain is approximately 1. At least we are not losing, okay? Because it's 1. So the input is like the output. Based on that, since AV is equal to 1, and remember, the output is at the emitter, and the input is at the base. So if the AV is equal to 1, that means that the VO is equal to V input. VO, which is at the emitter, is equal to V input. That's why they call it emitter follower. Emitter follower. Because the emitter just follows the input voltage. That's why they call it so. And by the way, this is maybe the most famous naming for it. Okay? Let's now explore its applications, okay, which are really interesting. So basic application number 5, basic application. When we need this common collector, or when we need a circuit with such properties. Okay, let's assume that we have a source. The source is big. I mean, I'm sorry, its voltage is big, so we don't need to amplify it. But this source has a very big internal resistance, very big, or much larger than the load that we want to feed voltage from that source to. So let's assume that we have a source, this source with our signal or our internal resistance equal to 100 kilo ohms, and the source signal voltage is 200 millivolt, and our load is equal to 1 kilo ohm. So let's see if we just connect this load to the source, what's going to happen? What will be the output voltage? So we have here the input, 200 millivolt, the internal resistance, 100 kilo ohm, and then our load here equal to 1 kilo ohm, 1 kilo ohm. What will be the output here? Remember, we have a source. This source produces some signal, some input, and it's our desire to feed our load with its full voltage. Let's see if this happens or will happen or not. So VO here is equal to 200 millivolt multiplied by 1 kilo ohm over 1 kilo ohm plus 100 kilo ohm. It's approximately 200 multiplied by 0.01 volt. So this is approximately 2 millivolt. So 1 over 100 of the signal reaches our load. That's that's really disastrous, we can say. That's really bad. So how can the common collector solve this problem to us? Okay, so the basic application for a common collector is to interface such horrible circuits together, such very high mismatching circuits together. A source with a very high internal resistance to a load with a very small resistance. Okay, so let's assume that we have so this is old, old-fashioned, for example. Let's now use, or let's call it bad connection. Yeah, let's call it bad or bad design. Bad design. In which you just connect the load to the signal, to the source. Now with common collector, let's assume that we have a common collector amplifier with our input equal to 100 kilo ohms, our output equal to 10 ohms, very small one, and the EV is equal to 1. Let's see if we use this amplifier to interface this signal source to the load, what's going to happen? What will be the output? So in the beginning, the output is 2 millivolt out of 200. So let's see what's going to happen. So let's draw the schematic of this example. So we have our signal here, the internal resistance. We have our V signal, which is 200 millivolt. Then we have our amplifier here. Remember, this is a symbol for the amplifier. AV is equal to 1. And here, the source sees our input. Then at the output, we connect the load, which is 1 kilo ohm. And here is 100 kilo ohm. And this is 200 millivolt. And the load sees RO. And of course, the magnified signal. Of course, there is no amplification here, just 1. So, good. We can remove this amplifier and put our input to the input signal and EV output and our output toward the load resistance. Good. So we have here the input terminals. V signal and our signal. And I will draw the amplifier model with red just to differentiate it. So our input, and here is the input. And towards the output, we have our O, AV, V input. Here is our O. Then we have the load. One kilo ohm. Good. Our input is 100 kilo ohm. Our signal is also 100 kilo ohm. And here is 200 millivolt. So first, basically, the input equal to 200 millivolt multiplied by 100 over 100 plus 100 multiplied by our input over our input plus our signal. So this is basically 200 multiplied by half, so 100 millivolt. Good. How about VO now? VO is equal to AV, V input multiplied by RL over RL plus RO. Let's substitute and see. AV is 1. The input is 100 millivolt. Our load is 1 kilo. So I will write it in ohms, 1000. Over 1000 plus 10. 10 ohms. RO is 10. Only 10 ohms. And what is 1000 plus 10? It's approximately 1000. So this is approximately 1. So the output is 100 millivolt. Now compare the two situations. In the beginning, without this common collector amplifier, the output was 2 millivolt. And now, with this common collector amplifier, even if without amplification, EV is 1, we got 100 millivolt, just because of our input and our output. That's why all the characteristics are important. Our input is important, our output is important, and the EV is important. Okay, so that's basically the basic application for common collector amplifiers. Is an interface circuits. And if we go now and speak practically, there is no source which with voltage generator or something with internal resistance of 100 kilo ohms. Actually, this input here, let's yeah, this input here, this signal actually comes from another amplifier. For example, a common emitter amplifier. Remember, the common emitter amplifier has high voltage gain, so the output voltage usually high, good, but it has high output resistance. Remember, common emitter has voltage gain larger than one, usually big, very good, but it has low R input, small R input, and the high R output. So the output will be high, good, but RO is high. So if you just connect a load to the common emitter, this will be bad. You will have something like, this example here. That's why we usually don't use one configuration by itself. We usually make, two stages, for example. So in order to amplify a signal at the input, we amplify it first using common emitter, then we put a common collector, then we put the load, not just one of them, to get benefit from both advantages, the advantages of the two circuits. Okay, so that's basically the common, common collector, common application, which is interface between a source which has a high internal resistance, and basically we said that this source usually another amplifier stage, common emitter, for example, and a small load. Okay. Now let's take. So let's draw this. So just as observation here. So practically, the V signal, R signal, source is usually or or might be, let's say, might be the output signal from another amplifier stage, common emitter, for example. So you have high output voltage, which is good, but high RO, which is bad. So most of the amplified voltage will not go to the load. That's why we bought the common emitter, common collector. I'm sorry. So if we draw that, so if you have a signal like this, for example, your mic, for example, your mic takes your voice and amplify it. So the mic can be imagined as a source, V signal, with internal resistance R signal. Then we magnify it using the first stage is a common emitter. With AV much larger than 1. But this guy has RO, common emitter, usually high. So based on that, we put another stage here, which is the common collector. It has AV equal to 1. That's good. but it has high input resistance. So this will be matched high with high here, and low. Then we draw the load. And low output resistance, RO, common collector is low or small. So we have matching here. The high input resistance, the high output resistance. If we connect it to RL, we might lose some of our amplified signal. So we put in between the common collector, so it can take most of this output to its R input. Then without amplification, it will deliver most of it to our load because RO is very small. Okay. And next lecture we're gonna talk about these multi-stage amplifiers and how we analyze them. They are easy, by the way. Good. So let's now take a numerical example just to imagine, what we have. Okay. So it's actually example in the book. It's a problem in the book. So let's get it. So here, copy and paste, insert, screenshot. Okay, so this is actually problem. So example. This is problem 6152 in Citrus book. Okay, so what's required here? So you have here the problem in the book. It gave you beta as a range from 50 to 200, and it asked you to solve the circuit once at 50 and once at 200. So we're gonna solve it at 100. So we assume that the beta is 100, and we're gonna solve it, at this only at this value. It should be at 50 and 200 should be the same. Same analysis, of course, not the same numbers. Okay. So what's required here is basically find AV, our input, our output, and AV. Okay. First, is this a common base or common emitter or common collector? Basically, the input is near the base. Here is the base and here is the input connected to the base, and the output is connected to the emitter. So it's a common collector amplifier for emitter follower. Okay. Let's remove that thing here. Okay. So let's solve it. Solution. Okay, so first DC analysis. In DC analysis, the capacitors are open. So we just remove this part and also remove this part. So the circuit will be reduced to the following one. RE, VCC equal to 5, and RB here, which is 100 kilo ohm. Let's call it RB. Yeah, and that's it. So IE from that loop here, IE is equal to. So let's do it in, not to confuse you. So what's flowing here is IB, and what's flowing here is IE. So IERE plus 0.7 plus IB RB equal to VCC. IE RE plus 0.7 and IB is IE over beta plus 1. And you can, ignore the 1. That's fine also. RB equal to VCC. So IE equal to 5 minus 0.7 over RE plus RB over beta plus 1. Beta is 100. RE is, it's a given 1 kilo ohm. And RB is 100 kilo ohm. So this will give you how much exactly? This will give us, I didn't write it down. No, yeah, 2.16 milliamperes. Once you get IE, you get RE. RE small is equal to VT over IE. Or you get RBI as well. So RBI is equal to RE multiplied by beta plus 1. So RE is VT over IE multiplied by beta plus 1. If you substitute, this will be 1168 kilo ohms. You can use RE small or RBI, that's very fine. Okay. Now we finished the DC analysis, so let's go now to the EC analysis. Oh, I'm not sure how to do that. Yes. So EC analysis number 2, EC analysis. In the AC analysis, short circuit on the capacitors, remove the DC sources. Okay, so if we did this, this will be shorted. This will be shorted. Capacitor, this will be shorted as well. So first start by the AC model of the transistor. So beta IB, here is RBI, here is IB, collector, base, emitter. So the collector is directly connected to the ground. The emitter is connected to the ground through two resistances, RL and RE, because now this is shorted, so this will be in parallel with this. R load, RE. And finally, the base is connected to the ground through, we have two branches here. Between the base and the ground, you have this RB. And the other branch is R signal and V signal. And before we continue, here is V input and R input, and in the future R output. Okay, so let's start first by R input. R input is it will be the resistance seen between these two terminals, this and the ground. So it will be RB parallel the resistance seen here. So let's call this our input dash. Okay. So if we assume this current is called I input, let's assume so. And here is the voltage V input. So R input dash equal to V input over I input. I input first is equal to IB. Basically, IB is flowing in that branch, so it's just IB. How about V input? So you just make a loop here and you will get it. So V input is equal to IB R by plus the current through here is IE, which is beta plus 1 IB flowing in both resistance in parallel. So the voltage here on RE or RL is the same because they are parallel, equal to beta plus 1 IB RE parallel RL. Let's now substitute this. So R input equal to RE capital parallel R input dash, which is V input over I input. V input is IB as a common factor. This will give us R by plus beta plus 1 RE parallel RL over IB. IB will go with IB. So R input equal to RB capital parallel R pi plus beta plus 1 RE parallel RL. Very nice. So let's have now a common sense for the numbers. So basically RB is 100 kilo ohm parallel. R by is 1168 kilo ohms plus beta is 100, so this is 101. RE is 1 kilo ohm. Parallel RL is also 1 kilo ohm. This is equal to 100 kilo ohm. Parallel 1168 kilo ohm plus 101 multiplied by half. So this is 100 kilo ohm parallel 1168 plus 50.5. So it's 100 kilo ohm approximately parallel to 50, something like 51 kilo ohms. So if we did the math, our input is 33.84 kilo ohms. Okay, which is big. I will say, after we finish, I will show you two situations. One with this circuit, and one if we just connect the load we have in the circuit directly to the input. We're gonna see both applications and how common collector actually solves, or enhances the performance of this circuit. Number two, RO. RO is the resistance seen by RL. So we're gonna remove RL and put a test voltage source, VXIX, some imaginary voltage source, and RO will be Vx over Ix. Good. So we're gonna draw the same circuit again. So I'm just copying it and paste. Good. So we're gonna remove RL. And put testing source Vx reducing Ix. And of course, we're going to cancel the source. So we have here one independent source, which is V signal. So we're going to short it. So RO will be Vx over Ix. Okay. I'm going to simplify it a little bit. So beta IB Vx Ix, and here RP capital and R signal are actually in parallel. So I will just draw one resistance, which is RB capital parallel R signal. Here is R bar. Here is RE. And the current here is IB. So from that loop here, from loop 1, what we have? We have Vx, and we have this voltage IB R bar, and we have this voltage IB RB capital parallel R signal equal to 0. We have one loop, three elements in that loop: the voltage source, R by, and RB parallel R signal. So Vx basically equal to minus IB as a common factor, R by plus RB parallel R signal. How about this node? At that node, you have Ix going into the node. You have beta IB also going into the node. You have IB also going into the node. And you have this current here, the current of RE, going out of the node. So this is equal to the current of RE. Current of RE is just the voltage across RE over RE. The voltage across RE is Vx. So Vx over RE. So let's remove Vx now and put its equivalent, which is minus IB multiplied by this factor here. So Ix plus IB beta plus 1 equal to minus IB R by plus RB parallel R signal over RE. So from this, Ix equal to minus IB. Let's take minus IB as a common factor. So this will lead us to beta plus 1 plus R by plus RB parallel R signal over RE. Okay. Good. Now let's find RO, because now V input or Vx and Ix both are function of IB. So we can divide them safely and IB will just go away. So RO is equal to Vx, which is minus IB R by plus RB capital parallel R signal over over Ix, which is minus Ib again. Then we have beta plus 1 plus R by plus RB parallel R signal over RE. Minus IB will go with minus IB. So this will give us R by plus RB parallel R signal over beta plus 1 plus R by plus RB parallel R signal over RE. Okay. Before we continue, remember in the first example that I gave for the common collector, RO was R by plus RB plus R signal. It was like this. It was R by plus R signal and both over beta plus 1. Okay, so we need to check now. We need to check if we are in the correct path or not. So to check on yourself, put R by equal to infinity, because in that example that we solved it in the beginning, there was no RB, which means RB is equal to infinity, and there was no RE, which means again it was infinity. So let's do it by one by one. So let's sorry. So one by one here. So let's do it with another color. If RE equal to infinity first. So what's going to happen? This is easy. If this is infinity, so this term here will just go away. So RO will be equal to R by plus RB parallel R signal over beta plus 1. Now second step, put RP capital equal to infinity. You know that if you have a parallel combination and one of the signals are infinity, the parallel combination will go to the second resistance. So RO, R by plus R signal over beta plus 1. We go back to the original value. So we are in the correct way. Okay? The only difference between this circuit and the circuit that we solved in the first example of common collector, there is RB, it's not infinity. There is RE, it's not infinity. So if we put infinity for RB capital and RE, we should get the same value that we got before. Good. Now let's have a sense of numbers. So let's substitute and see. So RO equal to all that stuff here. So let's substitute for the number and see what we're gonna get. So R by is 1168 plus RB parallel R signal is 909 kilo ohms. Beta plus 1 is 101 plus R by again 1168 kilo ohms plus RB parallel R signal against 909 over 1 kilo, which is, it's just write 1, which is R. Okay, so it's basically, around 10 in the numerator, divided by 101 plus 10 again. So it's like 10 over 101. Oh, sorry, 111 or 110. So it's approximately, 10 or something. So if you did the math here, the output will be 92.2 ohms, not kilo ohm, 92.2 ohms. Okay, which is very small. So the R input was around 33 kilo ohm or 34 kilo ohms, and here RO is in ohms, 92 ohms, very small. Okay. Finally, AV, number 3, AV. AV is equal to VO over V input. We need again the circuit, so let's paste it again here. Okay. So the input is the voltage from that point to the ground. Okay. And VO is here. is the voltage across RL or RE. So VO is equal to the voltage, sorry, the current through these two parallel resistors, which is beta IB, beta plus 1 IB, multiplied by RL parallel RL parallel RA. So this is VO. The input from that loop, which is still drawn here, this loop, let's call it loop 1. The input is equal to IB R by plus VO. And the VO is beta plus 1 IB RL parallel RA. So AV equal to VO is this thing here, beta plus 1 IB RL parallel RE over R by, and IB is common factor, plus beta plus 1 RL parallel RE. IB will go with IB. And if we substitute here, this will be 0.977. Approximately 1, right? It's very close to 1. 9.997. You can say 98. It's very close to 1. We finished. But let's now analyze the advantage that we get from adding this common collector. So the original case should be something like this. So let's have a line here. Let's examine the two situations with no common collector stage between the source and the load, and here with common collector between them. If we don't have a common collector, we have the source, V signal, and R signal, which is 10 kilo ohms, directly connected to the load, which is 1 kilo ohm. So VO here is equal to V signal multiplied by 1 over 1 plus 10, which is it's V signal over 11, which is around it's around 0.1 V signal. 10% only reaches, so 10% of V signal reaches the load. Now what happened after adding the common collector? So here is V signal again, 10 kilo ohms again, then our input, which is 33.84 kilo ohms. Then we have here AV, V input, and V input is here across our input, and the AV is 0.977. Then we have our O, which is 92.2 ohms. Then we have the output, which is 1 kilo ohm. Good. So first, V input is V signal, our input 33.84 over 33.84 plus 10 kilo. This is basically 0.77 V signal. Good. So AV, so here is V output. V output is equal to AV, V input. We have AV is 0.977, and V input is 0.77 V signal, so that's known. Okay, multiplied by R load over R load plus 92.2. So let's AV is 0.977. V input is 0.77 V signal, and R load is 1000 or 1 kilo ohm over 1 kilo ohm or 1000 plus 92.2 ohms. So if we do the math here, VO will be equal to 0.688 V signal. So here around 70% of V signal reaches the load, while here it was only 10%. So that's actually the advantage of having this common collector amplifier. Okay, guys, so that's all for the common collector. Okay, and next lecture we're gonna talk about multi-stage amplifiers, multi-stage BGT amplifiers, and then we finish the BGT amplifiers, and we go to another transistor, which is the NMOS transistor. Okay, and thank you very much, and have a great day. Bye bye.